my previous lecture we started this catenane. So, let us see. So, we have to have a rigid system, and let me show you with a hand. What do we want? We want, see, look at this. Here is a nitrogen, here is a nitrogen. What do we want? We want tetrahedral coordination. So, one nitrogen here. So, this side, and what is a tetrahedral? If I do like this, there will be a tetrahedral. So, 4 nitrogen will be tetrahedral. When two nitrogens are like this and other 2 nitrogens are perpendicular like this, then these 4 atoms are tetrahedral with respect to center. Okay. So, we want a metal ion to bind to 1 nitrogen, 2 nitrogen, 3 nitrogen, 4 nitrogen like this inside. And how it will happen? We took a rigid moiety. Here we have a rigid moiety from the previous class. Here we have a rigid moiety. Okay. So, if we react it with a metal ion which likes tetrahedral, nickel 2 plus likes square planar geometry. That means, with the nickel 2 what will happen? There is one unit and there is another unit, they will form like this, they will come tetrahedral. So, they will be square planar, 1 nitrogen, 2 nitrogen, 3 nitrogen, 4 nitrogen will be square planar, nickel will be here, no good. We want like this, only then it will become a catenane. So, which metal? Zinc 2 plus likes tetrahedral geometry. Zinc 2 plus has no ligand field stabilization energy. So, it generally likes zinc 2 plus maybe I will take a new page. So, I want tetrahedral. So, what will happen? Zinc 2 plus likes tetrahedral, but zinc 2 plus has a tendency to show more than 4 coordination. Sometimes it can show 6 coordination. Then if there are 6, then it will be all messed up. If I take nickel 2 like square planar, nickel 2 it will like square planar. Other metal ions they like octahedral, most of them. Then which one I will take? I will take copper 1, D10 system, copper plus, okay, copper 1 plus makes tetrahedral, and copper 1 plus does not have a tendency to show more than 4 coordination. So, therefore, when you make these compounds, you have to have knowledge of coordination chemistry also, okay, and properties of different metal ions. So, looking at this, we came to the conclusion that we will take a first row transition metal ion, and that is preferably that should be copper 1 plus, because copper 1 plus will become tetrahedral, and if that is tetrahedral, it will form like this. Okay. Imagine nitrogens are here, and this is phenanthrolene unit. Similarly, here nitrogen here and phenanthrolene unit. So, because it is tetrahedral, it has to be like this. Okay. It has to be like this, followed. So, therefore, I put copper 1 and copper 1 will form copper is blue. So, copper, so this is my copper, okay. This is my copper and nitrogen will, one nitrogen is here, another is here, that phenanthrone moiety, and it is come like this here, OH and OH, that was my compound, remember, and other two nitrogen, one will be here and here, and OH, OH, remember. Okay. So, now we have a tetrahedral, okay, tetrahedral coordination around copper. So, copper 1 here is acting as a kinetic coordination template. It is arranging the molecules in such a way that it binds in a specific manner, that is what we want. Okay. After this can be crystallized out also. Okay. Now, but crystal structure is not known. So, what I want now? I want to clip here and here. So, that is what I want. How to clip it? Now, while talking about clipping, it can clip here also and here also, okay, and there will be a mess up. So, if it clips here and here, then what you get? You get a huge macrocycle basically, okay. You get a huge macrocycle. If you remove this copper, you get a huge macrocycle, but that is what we do not want. We want catenane. So, what I will do? Whether it will form like this or it will go our desired way from here to here and here to here will depend upon this green reagent and the distance between these two. So, the distance between this one to here and this one to here will be very different from the distance from here to here and here to here. Okay. So, distance will be very different, all right. So, therefore, what I will do? Once this compound is formed, we will do molecular mechanics. From molecular mechanics, calculation. Molecular mechanics calculation, we can get optimum structure of this, and as soon as we get optimum structure of this particular compound, we know the distance between these oxygens, okay. Intra, we want intra, not inter. So, accordingly we choose our compound. So, after all these cartoon and all that, let me now start to the actual compound that was used. Okay. So, here I will write a phenanthrolene no put a Okay. Okay. So, and then I will react it with this compound can be easily made copper MEcN4 1 plus or maybe BF4 salt. Okay. This in acetonitrile, if I treat, I can easily get this compound copper okay. I can easily get this compound and okay. So, I can easily get and then after molecular mechanics calculation and finding out the distance between here and here and here and here, not here and here. Okay. This was the reagent chosen I CH2 CH2 O whole 4 CH2 CH2I and it react with a slightly basic condition cesium carbonate in DMF (60°C). These are all experimentally found and this was done by Jean-Pierre Sauvage, who is a student of first PhD student of Jean-Marie Lehn. The boss got Nobel Prize and his student also got Nobel Prize. Both of them got Nobel Prize. Okay. So, once you get this is a copper steel 1, remember. Okay. Then what will happening? Let me write. Okay, I have not written this part, remember that. Okay. So, now let me draw, let me put a let me put this. Okay. Okay. So, you write Hmm. Oxygen, oxygen 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And similarly here also. Okay. So, what did we get? We got this copper 1 complex, copper 1 plus complex. Now, here it is also connected, phenanthrolene, phenanthrolene connected. So, if we now reacted with potassium cyanide excess, potassium cyanide excess, it will take out copper 1. Okay. It will take out copper 1 and I am ended with what I am ended with, I am writing it. You should practice it at home, these structures. Okay. It is necessary to write this structure, so I am writing oxygen, oxygen 1, 2, 3, 4, 5, 6. Okay. Then 4 oxygen, 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 oxygen. I got this, and from the other one also I got the other one also. Usually we get okay. Okay, and then let me draw in a, or maybe it will confuse you. So, I will write okay, then whatever 1, 2, 3, 4, 5, draw here, whatever 1, 2, 3, 4, 5, 6. So, we have now made a particular catenane. This is known as 2-catenane. And is pretty good yield also. So, therefore, it is very important to understand that this is also done by kinetic template effect, and we have to look at the coordination tendency of the metal ion we are going to take. Once we get that complex, then it is easy to put it through. Okay. And once we got this catenate, is called catenate. This is catenane, and when a metal is bound to a catenane, is called catenate. Now, my question to you would be at this point, what will happen to this? Why these are two further? Because they were close to each other. Why they are further? Because of steric reason. And so, what is there in the middle? You have all ethers. So, remember crown ether? Crown ether likes alkali metal, alkaline earth metals. So, if I give an alkali metal ion here, it will go and bind here. And if I give a transition metal here, then what will happen? Especially copper one, then it will bind like this. That means this catenane, is not a fixed, but it is doing like this, It is like this when we give an alkali metal, and it is like this when we give a transition metals. So, it will be like this, always like this. It is quite interesting. And how to make molecular machines with these, we will go on and then we will discuss. Now, we can make 3-catenane also. 3-catenane, I will start from here. Okay. 3-catenane, I start from here. So, once we get this, okay. Once we get this, this one is now 2, this is not 4, but this is 2, this is 2, and then CH2, and this is not I, but it is a bromo compound, okay. Bromo. And similar method. Then let me draw a cartoon now. So, we have this and we have this. Again, we have this. Okay, and we have this. Okay, then what will happen? What happens? If you give like this with bromo, bromo reacts much less than iodo, that is why we want that. So, if we react it with bromo and this is 2 and 3. we give a mixture of 2, remember, let me draw n, where n equal to 2 and 3. So, we give 2 and 3, that means CH2 CH2O2 and CH2 CH2O3, 3 unit like that. That means the 2 different units. If I do like that, then what happens? With 3 it can bind here and it can bind here also. Then what are you getting? Then I am getting a compound of 1 macrocycle, another macrocycle, and here is another macrocycle. So, this is called 3-catenane. One, two, three. So, 3-catenane. So, that means we discussed 2-catenane and 3-catenane. This is based on metal ions. Okay. So, I stop here today. We will now see, can we synthesize catenane without the use of metal ions, and that is what will be our aim next in the next class. Thank you very much.